Hello students, welcome to the amazing platform of Physics Wallah PW English channel, my dear students. So today we are on the lecture 3 of electrochemistry. So my dear students, I hope whatever we have discussed till now, you are crystal clear with the concepts, because this chapter is all about concepts. If you are clear with the concepts, questions are super easy. So let's start the amazing session. What all topics are we going to cover today? We will be discussing about electrochemical series. What is electrochemical series? How is it used, right? Yes, and then we'll be talking about the Nernst equation as well. Okay, so today we are going to discuss a lot of conceptual parts, so you need to be a little fresh with your mind. Okay, so let's start the amazing session, my dear students. Before starting that, we will be discussing about she. What is she? She is a girl, right? Yes, we all know that girl is super powerful, right? Yes. The same way, my dear students, in electrochemistry, she is very powerful. Yeah, she stands for standard hydrogen electrode. Now we'll be discussing about this a little more. What is she? How will we be using this particular part? So now, my dear students, when we talk about standard hydrogen electrode, so we all know that we know that what is reduction potential, what is oxidation potential. So basically what happened is that we had to give some values so that we could find out that whether an element wants to get reduced as compared to the other, or it wants to get oxidized, because we know that oxidation and reduction is relative. If you have two elements and one of the element has comparatively more of the reduction potential, then that element will reduce and the other would get oxidized. So this means that this is always a comparative study. So for this, we needed to give some specific relative values so that we could find out that which of the following elements can be used as a cathode and which of the following can be used as an anode. So here comes the role of standard hydrogen electrode. What happened is, it is an electrode of hydrogen. Okay, so you had a electrode of hydrogen. So now what this hydrogen electrode did, this way you will have gas here. My drawing is very bad, I'm sorry. Okay, so here H2 gas, and this is your aqueous solution. So now, my dear students, what happened is scientists deliberately gave the reduction potential value of hydrogen to be 0. Now you have a specific value now, and you can give the values to the other elements relative to this particular part. Okay, yes. So what happened is, we all know that whenever we talk about an electrochemical cell, it has two different electrodes. It has the cathode, it has the anode, right? Yes. So I also told you that whenever you talk about an electrochemical cell, you can calculate its E naught of cell. You can calculate its E naught of cell. Yes, we can calculate that. And we also know that the E naught of cell is actually equal to E naught reduction potential of cathode minus E naught reduction potential of anode. So now, my dear students, just imagine if with the chemical reactions you can calculate E naught of cell. Yes, out of the two, if you know any one value, let us say you know this particular part, can you calculate the reduction potential of anode? Yes, ma'am, we can calculate. So this is the concept which was used to define the reduction potential values to all the elements using the standard hydrogen electrode. What happened is, you actually used, let me write it here, reduction potential of hydrogen, standard reduction potential of hydrogen was given to be 0. Okay, so now what happened, let's say you wanted to calculate the reduction potential for magnesium, right? Yes, what will you do? My dear students, you will create a cell. You have, let us say, this particular one electrode, and you will have another electrode. I'm just giving you an example. Okay, let's say this is your she. This is your standard hydrogen electrode. So I know very well that this is the reduction potential equal to 0, and this is my cathode. I am using it as a cathode. Okay, now the other would definitely be an anode. Yes ma'am, this will be an anode, and we want to calculate the reduction potential for magnesium. So now my dear students, what we will do, let's say this is your magnesium electrode. This is your magnesium electrode. This is the aqueous solution, right? Yes, you connected these two. Now when you will connect this, and you will get the E naught of cell. You will definitely get the E naught of cell. E naught of cell. I know that E naught of cell is given, let's say it is given to be X. Okay, yes. Now my dear students, how can we find out that what is the reduction potential of anode? That is your magnesium. Now see, if I talk about the reduction potential here, this will be from H plus to H2. If I talk about the reduction potential of this particular anode part, this would be Mg2 plus 2 Mg. Now, if you are supposed to calculate the E naught of cell, how can you calculate it? We know that E naught of cell is equal to E naught reduction potential of cathode minus E naught reduction potential of anode. I know that E naught of cell is calculated, which was X. I know that my cathode is She, standard hydrogen electrode. So the reduction potential will be 0. So here it is 0 minus E naught reduction potential of anode. So from here we can say that E naught reduction potential of anode will be equal to minus X volt. So this is how you can use She and calculate the reduction potential of various other elements, right? Yes. So this is the major use of She actually contributed itself that, okay, fine, I'll take the 0 value so that you can give values, relative values to all the other elements. Okay, yeah. So this is what happened. If you want to write it, you can write it, and then we'll move forward. Now my dear students, based on these values, okay, just write it. Let's move forward. Based on these values, whatever the values came out, a series was made, and this series was actually known as the electrochemical series. This series was actually known as the electrochemical series. Now, just see, here is your hydrogen. Here is your hydrogen. That is your, here I know that the reduction potential will be equal to 0. Now, the reduction potential of all the other elements were calculated and they were arranged in some specific way. And that specific way was that after hydrogen, as we move down the series, my dear students, reduction potential, that is E naught of R, increases. As we move down the series, reduction potential will increase. Okay, so this particular case, we can say that as we will move top to down, the reduction potential will increase. Okay, yes. Now you need to understand a little more. This reduction potential value is 0, and since it is increasing, so I can say that down the reduction potential values would be positive. But if we talk about here, my dear students, then the reduction potential values were actually negative in value. They were negative values. Okay, yes. So this is how we would be studying the electrochemical series. This is the first part. Now let's talk about the other part. What will happen if I move from top to bottom? If I move from top to bottom, I can say that oxidation potential increases. Okay, now we can say that from top to bottom, the oxidation potential is increasing. And what is oxidation potential? Oxidation potential is the tendency to get oxidized. Now we will be discussing about these major terms, right? Yes. So now let's discuss about these major terms, my dear students. If we talk about the reduction potential, I hope we all remember that reduction potential is given by E naught of R. And what does reduction potential mean? Reduction potential means that the tendency to reduce itself. An element which has a tendency, more of the tendency to reduce itself, that is, more of the tendency to gain electrons, the more will be its reduction potential. So, reduction potential is tendency to reduce itself. Okay, and If I talk about the oxidation potential, then oxidation potential, what will be the oxidation potential? Let's define oxidation potential, my dear students. Ma'am, oxidation potential will be the tendency to what is what is oxidation potential? Tendency to oxidize itself, that is to lose electrons. So this is tendency to oxidize itself. And also my dear students, we studied that always the reduction potential is the negative of the oxidation potential. So if an element has a higher of the reduction potential, then definitely its oxidation potential would be less, right? Yes. So this is how you define the reduction potentials and oxidation potentials. If an element wants to get reduced, if it wants to gain electron, then it will have a higher reduction potential. If an element wants to get oxidized, it wants to lose electrons, then it will have a higher oxidation potential, right? Yes, perfect. I hope this is clear with you. This is the first thing that we can interpret from the electrochemical series. Now, the other thing which we can interpret from the electrochemical series is a very important term, which is the oxidizing agents and reducing agents. Okay, so now let's discuss about this. If you talk about the oxidizing agents, now let's talk about and understand this, because most of the students get confused in the oxidizing agent and reducing agents. Now see, how are you going to understand this particular part? You can understand this particular part just by understanding that if you talk about an agent, who is an agent? Who works for others. An agent doesn't work for himself, right? Yes, an agent works for the others. Somebody will hire an agent and then he or she will do a particular work. This means that agent works for others, not for themselves. So if you have a oxidizing agent, then what oxidizing agent will do? It will oxidize it, definitely, but not itself. It will oxidize the other, and if it is oxidizing the other, this means that it itself is getting reduced. So you need to understand the basic meaning of oxidizing agent. Oxidizing agent is an agent which oxidizes the other and itself get reduced, right? Yes. So this is the first thing that we need to understand, that oxidizing agent oxidizes itself. Oxidizing agent oxidizes others and itself gets reduced. Now, you have to understand this particular part again. If you are talking about an oxidizing agent which oxidizes the other and itself gets reduced, then the more it will get reduced, the more it can oxidize the other. I hope you're getting this. The more it will get reduced, the more it can oxidize the other. This means that a good oxidizing agent needs to have a high value of reduction potential, So we can say that for a good oxidizing agent, it should have higher reduction potential. So if an element has a higher reduction potential, if it has a high reduction potential, means that it itself wants to get reduced, and the more it wants to get reduced, the more it will oxidize the other, and the better the oxidizing agent it will be, right? Yes. So this is the thing which we need to understand. Okay, I hope you're clear with the oxidizing agent. If you're clear with the oxidizing agent part, my dear students, then I hope you can give me the correct definition of reducing agent. You can give me the correct definition of reducing agent. Now understand this. What is a reducing agent then? A reducing agent would be an agent which will reduce the other and itself will get oxidized, oxidized, right? Yes, the more itself gets oxidized, the more it has a tendency to reduce the other, and the better the reducing agent it will be, right? Yes, so from here we can say that reducing agent reduces others and itself gets oxidized, right? A better reducing agent will reduce the other and itself will get oxidized. Now since it will get oxidized, the more the oxidation potential, the better the reducing agent. So the more the oxidation potential, the better the reducing agent. Try to understand this with this particular concept only. Otherwise, if you will try to memorize it, you will definitely get confused. Okay, so try to understand this. Okay, yes, I hope you're clear with the oxidizing agent and reducing agent part. So now if we move to the electrochemical series, can you tell me which top or the bottom, where will I get better oxidizing agents? Where will I get better oxidizing agents? Okay, now let's see. If I am talking about a better oxidizing agent, this means that, ma'am, you want an agent which can oxidize the other. So it will get reduced, and since it will get reduced, this means that it should have a higher reduction potential. The more the reduction potential, the better will be the oxidizing agent, and we know that reduction potential increases down the group. So here we will get a better oxidizing agent. Can I write it OA? Yes, let me write it OA. So here you will get better oxidizing agents. And if you talk about reducing agents, then you know that a reducing agent will reduce the other and itself will get oxidized. And since it will get oxidized, this means that it should have a higher oxidation potential. The more the oxidation potential, the better the reducing agent. So this means that here you will get the reducing agents, because from top to bottom you get higher oxidation potentials. Right? Yes. So this is the thing which you need to understand, because all of the questions are asked from this part, this electrochemical series. This is the most important thing which you need to understand. Right? Yes. I hope you are clear with this particular part. Now, my dear students, after this you also come across two very, very important words. And what are those words? Those words are reducing power and oxidizing power. You have reducing power and you have oxidizing power. Now let's discuss about reducing power and oxidizing power. What is reducing power? Now, you know that what will be someone's power? If someone has a very high reducing power, this means that the person can reduce the other very high with very much of the power. Okay, we can say that. Yeah. So for the reducing power, what do you need? You need that the other should get reduced. Right? The more you will have a reducing power, the more the other will get reduced. The more itself will get oxidized, right? Yes. So we can say that more the oxidation potential, the more it will get oxidized, and the more the oxidation potential, better the reducing power. I hope this is clear with you. I hope this is clear with you. The more the oxidation potential, better the reducing power. Now let's talk about oxidizing power. I hope you can answer this yourself. So pause the video, try this yourself, and then you'll have to see what ma'am is giving the answer. If you talk about oxidizing power, this means that the power to oxidize other. If you are oxidizing the other, you're getting reduced. So you should have a better reduction potential. So you will say more the reduction potential, better the oxidizing power, power. Right? Yes. So this is how you will understand the reducing power and the oxidizing power. Okay, so these are the few things which you need to understand about electrochemical series, because mostly these questions are asked. Okay, one more important thing which is generally asked, now we are going to discuss about that, and that is, my dear students, let us say you have a metal, let us say you have two metals. Okay, I'll just give you a solution. Now you have, let's say, an aqueous solution. Let's say you have an aqueous solution of MsO4. You have an aqueous solution of MsO4. Okay. Now, my dear students, you added some X metal to it. You added some X metal to it. Now you will have to understand this, and then we'll move forward. Okay. If I talk about the oxidation states here, I know that this is 0 and this is in the +2 oxidation state, right? Yes. So now I just want to ask you whether this particular reaction will happen or not, whether this particular reaction will take place or not. I am giving you a few values which you need to understand. The value is you have X2 plus 2X equal to, let us say, minus 2.3 volt, and you have E naught of M2 plus 2M equal to, let's say, plus 2.4 volt. Okay, now you have to understand this part. Okay, I just want to ask you whether this reaction will take place or not. Okay, so now, my dear students, if this reaction takes place, let's assume that this reaction is taking place. If this reaction is taking place, then ma'am, the reaction would be XSO4 plus the metal. Right? Yes. And if I see here, what is happening, my dear students, from 0 to +2 state, here +2 state and this is in 0 state. So I can say that what is happening here, ma'am, here oxidation is taking place. And ma'am, here what is happening? Reduction is taking place. I hope we can find out the oxidation and reduction part now. Right? Yes. You know that oxidation is taking place here, reduction is taking place here. This means that for this particular reaction to happen, the metal should have a higher reduction potential. Your M2 plus should have a higher reduction potential, right? Yes. So what we need to see is, for this particular reaction to take place, the reduction potential of the metal M should be more. If I see here, I have both of them. See, this is also reduction potential and this is also reduction potential, right? Yes. Ma'am, I can see that the reduction potential of M2 plus to M is plus 2.4 volt and the reduction potential for X2 plus to X is minus 2.3 volt. Can I say that the oxidation potential of X to X2 plus will be equal to plus 2.3 volt? Yes, ma'am, we know that it is the opposite of it, right? Yes. So I see that the reduction potential of this particular thing is more. Yes, ma'am. So this will want to get reduced. So this will get reduced, my dear students, and this reaction will take place. So reaction will take place. And in this reaction, what happened, my dear students? In this reaction, ma'am, this metal X had a higher oxidation potential. So it actually displaced the metal. M and the reaction took place. This is what actually happened. This is an example of displacement reaction, right? Yes. Now I want to change the question. Now let's change the question. Again, you have X plus you have MsO4, right? And now I want to ask you whether this reaction will take place or not if you have E naught of M2 plus to M equal to minus 2.3 volt and you have E naught X2 plus to X equal to plus 2.4 volt. Now what I did, I just changed the values. Now tell me whether this reaction will take place or not. Now let's see, will this reaction take place or not? I know that for the reaction to take place, the reduction potential of this particular thing should be more and the oxidation potential of this metal should be more. Only then it will displace the aqueous solution, right? Yes. If I see, then X oxidation potential would be E naught of X to X2 plus. This would be the oxidation potential and this will be minus 2.4 volt. Ma'am, the oxidation potential is coming out to be less, right? Yes. So since the oxidation potential is less, so this will not be able to displace this, and no reaction will take place, So from this we can say that if a metal has a higher oxidation potential as compared to the aqueous solution ion, then it can displace it from its aqueous solution. Right? Yes. So for the displacement to happen, the metal should have a higher oxidation potential. Right? If you understood this, it is very good. If you haven't understood it, now I'll explain you with the electrochemical series. See, I know that the elements above have a higher oxidation potential as compared to the elements below. For example, if I talk about calcium and sodium, I can say that calcium has a higher oxidation potential as compared to sodium, right? Because top to bottom reduction potential is increasing, so oxidation potential is decreasing. So I can say that calcium has a higher oxidation potential than sodium. So my dear students, your calcium can displace your sodium. Your calcium can displace your sodium from its aqueous solution because calcium has a higher oxidation potential. So from this, what we can say that in an electrochemical series, the elements above can displace the metals below in their aqueous solutions. As they have higher oxidation potential. Right? Yes. So this is how you can understand. If you want to understand the concept, you can understand the concept. If you want to just memorize it, that in an electrochemical series, if the metal is above the given metal of the aqueous solution, then the above metal, if it has a higher oxidation potential, it definitely can displace the metal which is below it. Okay, yes, I hope you're clear with this concept. So if you want to write it, you can write it, and then we'll move forward. You can write this, you can write this, and then you can write this. This is the most important part. Okay. Okay. Let's move forward now, my dear students. Let's try a few questions. And understand the concepts. Now, the question says, arrange the following metals in the order in which they can displace each other from the solutions of their salts. So I know very clearly that the metal which is above can displace the metals below it from their aqueous solutions, right? Yes, because it has a higher oxidation potential. We just understood it. Now, you have aluminium, copper, iron, magnesium, and zinc. I know that copper is somewhere here. Now, let's see the electrochemical series. You have copper here, and then if you talk about, you have aluminium, iron, then you have aluminium, zinc, iron. Okay, then you have magnesium, aluminium, zinc, and then iron, right? So from here, what we can say is that magnesium can displace all the four. Right? But aluminium can displace only these three. It cannot displace magnesium because aluminium will have a lower oxidation potential as compared to magnesium. You have to give the array or metals in the correct order in which they displace each other. So ma'am, magnesium displaces the most, and then aluminium, and then zinc, and then iron, and the last would be copper. Copper will not be able to displace any of the following because it has the lowest oxidation potential and the maximum reduction potential. I hope this is clear with you. Perfect, my dear students. Let's move forward to the next question. Now you have a question. Try to understand this question and try to solve this question. Pause the video, try yourself, and then you will have to see ma'am's approach. Okay. What does the question say? Given the standard electrode potentials, now you're given the standard electrode potentials. It could be reduction potentials, it could be oxidation potentials. You have to just see the E0 values and guess. You have to arrange these metals in the increasing order of reducing power. My dear students, it is said that you have to arrange them in the increasing reducing power. I know that for more reducing power, what do you need? If you are reducing someone else, you yourself are getting oxidized, and if you are getting oxidized, so you need to have more of the oxidation potential. So for more the oxidation potential, better will be the reducing power. Okay, yes, so we just need to see the maximum oxidation potential and then we'll give the correct order. If I see here, is this reduction potential, my dear students? E0 of K plus 2K. Just see the direction. No ma'am, this is given to be the reduction potentials, right? And I know that E0 of oxidation potential is equal to minus of E0 of reduction potential, right? So you are given the reduction potential. Can you calculate its oxidation potential? Yes. So this was the reduction potential. What will be the oxidation potential from K to K plus? Just put a negative sign. So minus minus plus 2.93. Let's talk about the other part. If you see, this is also a reduction potential. You need a oxidation potential. So E0 of Ag to Ag plus will be equal to 0.8 volt. Let's talk about this, my dear students. Again, this is your reduction potential. You need a oxidation potential. So E0 of Hg to Hg plus 2 plus will be minus 0. Oh, I haven't put the negative sign now. Minus 0.8 volt. This would be minus 0.79 volt. Okay, let's talk about this particular part. You have E0 of, again, reduction potential. You need the oxidation potential. So this would be Mg to Mg2 plus, and this value would be plus 2.37 volt. Okay, so this would be plus 2.37 volt. Again, my dear students, what is this? This is again reduction potential. You need the oxidation potential. So E0 of chromium to chromium 3 plus will be equal to minus plus 0.74 volt. You need to give the correct order for the reducing power. So maximum oxidation potential will have the most reducing power. Let's see, this is plus 2.93, then you have plus 2.37. So first would be E0 of K to K plus, then you will have, can I name them 1, 2, 3? It would be a little bit easier for me. This would be 1, 2, this would be 3, then 4, and then this will be 5. Okay, now we can arrange them very easy. First, then I think this one, fourth. Okay, then fourth. After fourth, you have fifth. After fifth, my dear students, you have minus 0.79, minus 0.8, which is a bigger value, minus 0.79. So third, and the last would be second. This is how you will solve this question. Okay, so you need to understand how you have to solve the questions. Perfect. Let's move forward to the next question, my dear students. Next question is here. Just see the question. Depict the galvanic cell in which you are given a reaction and you have to give the galvanic cell. Okay, perfect. We have to solve all single parts. Let's start this question. Which of the electrode is negatively charged? First of all, my dear students, you are given galvanic cell. So in galvanic cell, we know that anode is negatively charged. Now you just need to understand that which part is anode. Okay, if I talk about this reaction, I can write this reaction. This would be zinc solid, gives me 2 Ag plus. This gives me zinc 2 plus, and then 2 Ag. Okay, if I see oxidation and reduction, I can say that from here to here, what it is happening, it is reduction. No, oxidation, and this is reduction. So this is anode and this is cathode. I hope you're clear with this. Yes, ma'am. So now just check. My dear students, which is your anode and which is negatively charged. Ma'am, we know that zinc to zinc 2 plus is our anode and this is negatively charged. So you have given your first answer. Let's talk about the second. Second is the carriers of the current in the cell. You have to give the carriers of current in the cell. In the cell, my dear students, it is not asking you the carriers outside the cell. In the cell, you have the carriers ions. So the answer would be ions. It would free ions. The answer would not be electrons because it has specified that you have to give the answer in the cell, not out of the cell. Okay, let's talk about the third part. Individual reactions at each electrode. So easy. We have found out cathode, and at cathode reduction takes place. Reduction from Ag plus to electron will give you Ag. And if you talk about anode, anode oxidation takes place. Then zinc will go into zinc 2 plus 2 electrons. Zinc will go into zinc 2 plus 2 electrons. So this is how you will solve this particular question. I hope you're clear with this. You want to pause it, pause, write, and then we'll move forward. Let's move forward to the next question. What does the question say? The question says that how would you determine the standard electrode of the system Mg2 plus 2 Mg? I have just discussed this part. In fact, I made you understand the standard hydrogen electrode taking this particular example, right? Yes. So I hope you can answer this question. Yes, you can answer this question. So perfect. This would be your homework. Let's move forward to the next question. Next question says, can you store copper sulfate solution in a zinc pot? Can you store copper sulfate solution in a zinc pot? So this means that you have copper sulfate solution and you have zinc here. Okay. So now you just need to tell me that whether you can store it or not. See, you have the zinc metal, you have a aqueous solution of copper sulfate. If the reaction will take place, we cannot store. If the reaction is not taking place, we can store, right? Yes. As long as the pot is not reactive with the solution, we can store it. So we just need to see that whether the reaction will take place or not. Let's see. I have zinc, the metal, and I have copper 2 plus. I know that for the reaction to take place, the oxidation potential of zinc should be more than the oxidation potential of copper. This true or not? You just have to go to the electrochemical series, and if you see in the electrochemical series, my dear students, the oxidation potential of zinc is more than the oxidation potential of copper, and since it is more, this will displace and will give you ZnSO4 plus copper, and this means that storing copper sulfate solution in zinc pot is reactive, and since it is reactive, we cannot store it, right? Yes. So we can say that zinc will displace copper from its aqueous solution. So we cannot store copper sulfate solution in zinc pot. So this is how tricky questions are generally asked. This is how tricky questions or conceptual questions are asked. I hope you're clear with this. Let's move forward to the next question. So next question is on your screens. Consult the table of standard electrode potentials and suggest 3 substances that can oxidize ferrous ions under suitable conditions. How are you going to do this? See now, my dear students, it says that you have to give 3 elements which can oxidize ferrous ions. You have to oxidize the ferrous ions, right? Yes. So this means that you want that iron, you want that ferrous ion should get oxidized. It should get oxidized. So if you want this to get oxidized, so you definitely want that the oxidation potential of this should be more than whatever elements you're taking. Yes. So you just need the elements which have a lower oxidation potential than this, which has a higher reduction potential. So in electrochemical series, my dear students, all the elements which are below iron from here to here will have lower oxidation potential as compared to iron, and since it will have lower oxidation potential as compared to iron, iron will get oxidized and the other metal will get reduced, and this is what you want. So you just need to understand what the question is asking, and according to that you can answer, right? Yes. So I hope you're clear with this part. Very good, my dear students. Perfect. Let's move forward to the next question. So the next question is on your screen. You have to try this question. This is a very, very important question. Again, such questions are asked in your exam. So the question says that the standard reduction potential values of three metallic cations are, so you are given three metallic cations X, Y and Z, and you are given the reduction potential values as 0.52, minus 3.03 and minus 1.18. Okay, yes, are these values. The order of reducing power of the corresponding metal is. So now understand this. I know reduction potentials and I want reducing power. So if I talk about the reducing power, this means that the other element will get reduced. The more the reducing power, the other element will get reduced. If the other element is getting reduced, myself, I am getting oxidized. So can I say that more the oxidation potential, better will be the reducing power? I hope this is clear with you. So you just need to find out the oxidation potentials. You are given reduction potentials. Oxidation potential will be equal to minus of reduction potential. So this would be minus 0.52, this would be plus 3.03 and this would be plus 1.18. So just arrange in the correct order of the oxidation potentials. So which has the highest oxidation potential? Y. So it will have the highest reducing power. Then Z, and the least would be A. So your correct answer would be X. So your correct answer would be YZX. YZX, option 1 will be your correct answer. So this is how you will be solving these questions. Okay, perfect. I hope you're clear with this concept. Now let's move forward to the next question. Next question is on your screen, my dear students. Try to do this question yourself. The question says that EMF of cell reaction, you are given a reaction and you are given the EMF of that cell. Also, you are given E0 value of one electrode. You have to give the electrode value of the other. It is the most easy question which you can do today. Okay, so you need to pause the video and try this question yourself. Okay. See, first and the most important thing which you all will do after seeing this question is, you will see which of the following is the anode and which of the following is the cathode. So if I see Ag plus to Ag, this is reduction. Since this is reduction, this is cathode, and from Cu to Cu plus, this is oxidation, and since it is oxidation, so this is anode. So I got my anode and my cathode. Okay, yes. If I talk about the E0 reduction potential of cathode, what will it be? What is cathode? This particular part, and you need the reduction potential. So you need E0 of Ag plus to Ag, because this actually gives the direction of reduction potential. If you talk about the E0 reduction potential of anode, what is your anode? Copper part. So this time E0 copper 2 plus 2 copper, right? This will be your reduction potential for anode, right? Yes. I also know that E0 of cell is equal to E0 of cathode, which is Ag plus 2 Ag minus E0 anode copper 2 plus 2 copper. Yes, perfect. Now E0 of cell is given to be 0.46. So this value is given to be 0.46. If you talk about Ag plus 2 Ag, you need to calculate this. So this would be E0 of Ag plus 2 Ag minus, are you given E0 value of copper 2 plus 2 copper? Yes ma'am, it is 0.34. So this will be 0.34. So E0 of Ag plus 2 Ag will be equal to 0.46 plus 0.34. This is 10, 4, 5, 6, 7, 8. So 0.8 volt will be your correct answer. So 0.8 volt, that is option A, will be your correct answer. Option A will be your correct answer. I hope you are clear with this. This was the most easy question which could have been asked. So pause the video and try this question. Okay. Yes. Let's see. You have another question. Can I give you this question as your homework? because it is exactly the same type of question we did earlier. Okay, so this will be a homework question. Try to do this question yourself and then we'll move forward. Now let's move forward. Now we will do a few little more questions and then we'll start a new topic. So now, my dear students, what are we going to discuss? See, the question is here and such type of questions are generally asked. So what the question says is, you are given E naught values and you have to give the strongest oxidizing agent and the strongest reducing agent. Okay, I'll give you a few questions as your homework as well, so don't worry. So now if we see the first part, I just want to explain you this particular part. If we talk about this particular part, you have from Br2 to Br negative. So can I say that here you will have a half electron and this is actually reduction? So can I say that this is the reduction potential values? This is reduction potential. Let's talk about the others. Cl2 to Cl minus. What is this? This is also reduction potential value. If I talk about this, F2 to F minus, again ma'am, reduction potential values, and I2 to I minus, again reduction potential values. If you need the oxidation potential values, then what do you want? You can say that for E naught from Br negative to Br2, your value would be minus 1.06. Similarly, E naught from Cl negative to Cu, your value would be minus 1.36 volt. Let's write this also from E naught F negative to F2, your value would be minus 2.25 volt. And for E naught I negative to I2, your value would be minus 0.53 volt. These all are your oxidation potential values. Okay, we are clear till now. Now, it is asking you, you have to give the strongest oxidizing agent. Now, what does oxidizing agent means? Means that an agent who will oxidize the other. If it will oxidize the other, it itself will get reduced. So, can I say that more the reduction potential, better will be the reducing agent? Sorry. More the reduction potential, better would be the oxidizing agent because it will get reduced and oxidize the other. Yeah. So what you want? You want the maximum reduction potential. So we'll be discussing about this. We'll see these reduction potentials which has the maximum value plus 1.36. Yes ma'am, this particular value is the maximum. Now the question is, out of F2 and F minus, which is actually your oxidizing agent? Since the reaction takes place from F2 to F minus plus half electrons, my dear students, so your F2 is the strongest oxidizing agent and not F negative. So your answer would be F2. F2 will be your strongest oxidizing agent. If you got this particular part, now try to solve the reducing agent part. Now for reducing agent part, what will you say? Ma'am, we would say that if we are talking about the reducing agent, then it will have a tendency to reduce the other and itself will get oxidized. And if itself will get oxidized, this means that it should have a higher oxidation potential. So higher oxidation potential, better the reducing agent. Now the question is that which we'll see these oxidation potentials, right? Which will be the maximum value? First, let's see that. All values are in negative. So the least negative value would be the maximum value. So this is the maximum value. Right? Yeah, this is the maximum value. Now the question is, out of I negative and I2, which is your reducing agent? If you talk about the reaction would be something like this. So this I negative is actually your agent because it is undergoing oxidation, right? Yes. So which of the I negative or I2, which is your reducing agent? I negative is your reducing agent. So you will say that I negative is my reducing agent here. So this is absolutely right that you will find the oxidation potential and reduction potential, but you also need to find out that which species will act as your oxidizing agent and reducing agent. I hope you're clear with this. The one which is undergoing the oxidation or the reduction, that particular species will be oxidizing or reducing agent. Okay. Yes, I hope you're clear with this. If you want to write it, I'll move aside, pause the video, write, and then we'll move forward. I hope you're clear with this. Let's move forward to the next question. The next question is on your screens. Metal and the reduction potentials are given. Metal and reduction potentials are given. You have to, okay, the question is incomplete. So let's write the question. Arrange in increasing order of, and arrange in according to the oxidizing power. This is your homework. Okay, this is your homework. You will have to try this question yourself. I have given you a lot of questions like this. So now this will be a homework question. You will have to do this question yourself. Okay, yes. The next question again will be your homework. We've just done a question exactly same. You can find the strongest reducing agent and also you can find the strongest oxidizing agent also. Okay. Strongest oxidizing agent. You have to give me the strongest oxidizing agent. Okay, clear? Very good. Perfect, my dear students. Now we will be discussing a very important thing, which is the Nernst equation. Nernst equation. What is Nernst equation, my dear students? This is just the introduction. Now I'll give you the Nernst equation. See, what happened is when I told you about the standard EMF of the cells, when I talked about the standard EMF of the cell, what actually happened was, my dear students, we actually fixed a few values: the temperature, the pressure, and the concentrations. We fixed these three values, right? Yes. But in the real world, are these values fixed? No, ma'am, these are not fixed. This means that we need to understand that how we can calculate the EMF of cells if we are not given the standard conditions. Apart from standard conditions, how we can calculate the EMF of the cells. Okay, yes. So this is what we will be discussing in the Nernst equation. What Nernst did is he gave us a equation where we can calculate the EMF of cell at various temperatures and pressures and concentrations, at various pressures and temperatures and concentrations. Okay, yes. So now we will be discussing that particular part. Okay, now let's write the Nernst equation. Just check the spelling. I am sorry if it is wrong, but I guess this is right. Okay, let's talk about Nernst equation. What Nernst equation actually was, you know that E of cell, this time this is not standard EMF of cell, this is E of cell. This is E of cell. Okay, so E of cell was given as E naught of cell minus 2.303 RT upon NF log Q. This was your Nernst equation. Now I'll explain you each and every part. Don't worry. Now I'll explain you each and every part. What does each and every part here denotes? Okay. So from here, if I talk about E of cell, what is E of cell? EMF of cell. Normal EMF of cell, not at standard conditions. It is normal EMF of cell, which you will be calculating. What is E naught of cell? This was the standard EMF of cell which we calculated. Standard EMF of cell. This is the standard EMF of cell which we were calculating at the standard conditions. What is R, my dear students? R is your gas constant. And the value used here of gas constant is, are we supposed to calculate? No, you need not the R value. You need not remember the R value. So let's write it as R is the gas constant. Okay. If you talk about T, T is your temperature, my dear students. If you talk about N, N is the moles of electron transferred. And if you talk about F, F is Faraday. F is Faraday and it is equal to 96500 Coulomb. What is Faraday? Charge of 1 mole of electron. Charge of 1 mole of electron. Okay, yes. Now, my dear students, what is Q? Q is of most importance, which is your reaction quotient. This is your reaction quotient. Now let's discuss. Now when your Nernst gave this equation, he supposed that we know that R is a constant value. Yes, we generally take reactions at room temperatures, at one particular temperature. So he fixed the temperature as well. And we know the value of Faraday, it is 96500 Coulomb. Okay, yes. So what he did, he gave a better simplified version of Nernst equation, and that better simplified version of Nernst equation was E of cell is equal to E naught of cell minus 0.059 upon N log Q. Okay, so this was the better, most simplified form which you will be using in your questions. So you need to memorize it. You need to memorize it. Okay. So E of cell is equal to E naught of cell minus 0.059 upon N log Q, where E of cell is the EMF of the cell, E naught is the standard EMF of the cell, N is the moles of electrons that will get transferred, and Q is your reaction quotient. Now you need to understand the reaction quotient. How are you going to calculate the reaction quotient? My dear students, when you studied the equilibrium chapter, I hope you remember a word which was reaction quotient. How you used to calculate the reaction quotient? Let us say you have a chemical reaction. Let us say you have a chemical reaction AA plus BB gives you, there is an equilibrium CC, and then you get D. The equilibrium is not achieved, but this is the reaction that is taking place. Okay, now my dear students, if you talk about the equilibrium constant Q, then that will be equal to the concentration of your products raised to the power their stoichiometric coefficients divided by the concentration of the reactants raised to the power their stoichiometric coefficients. So you will have the concentration of C raised to the power C, then concentration of D raised to the power D divided by concentration of B raised to the power B and concentration of A raised to the power A. So this is your reaction quotient. Right, when the reaction hasn't achieved the equilibrium, achieved the equilibrium, this is your reaction quotient. Okay, yes, I'm again and again telling you. So if you want to write it like this, you'll understand it better that the equilibrium hasn't been achieved yet. So this is how your reaction quotient is written. Right, yes. So I hope you're clear with this particular part. Now let's move forward. So this is the EMF of cell. This is the expression, and you will put the values in it, and you can calculate the EMF of cell at various different conditions, at various concentrations of your reactants and products. Okay, yes. Now the question arises that, ma'am, can we apply the Nernst equation only on the net cell reactions, or we can apply the Nernst equation on any half cell reaction as well? So I just want to tell you that you can apply your Nernst equation on any net cell reaction also, as well as you can apply it on half cell reactions as well. So this is the most important part, Nernst equation. Where can we apply this particular equation? See, you can apply it on half cell reactions, and also you can apply it on net cell reactions. Let's talk about half cell reactions. Let's take an example. Let's take a reduction reaction. Let us say you have some M metal, which is Mn metal, which is getting reduced, gaining N electrons, and it is giving you M solid. Okay, so this is your half cell reaction. It can be oxidation reaction, it can be reduction reaction, it doesn't matter. You can calculate the reduction potentials and oxidation potentials with using the Nernst equation. Okay, yes. So if you want to apply the Nernst equation here, then what will it be? E of reduction potential. Now this will not be the standard value. So E of reduction potential will be equal to E naught of reduction potential of Mn2 plus Mn plus to M, right? E is equal to E naught of cell minus 0.059 upon How many moles of electrons are being exchanged? N moles of electrons are being exchanged. So here N value will come log of, my dear students. Now you need to remember that in reaction quotients for pure solids and pure liquids, you never use their concentrations. You consider them to be constant. Only and only aqueous ions concentration were used. Since this is a solid, it is a pure solid, so we will not take its concentration. So products concentration 1 divided by, in reactants we have Mn plus, so the concentration of Mn plus. So this is how you apply Nernst equation on a half cell reaction and calculate the reduction potential. Same way, if you apply this on an oxidation reaction, then you can calculate the oxidation potential as well. Now let's talk about a net cell reaction. So if you have a net cell reaction, then you will say that E of cell will be equal to E naught of cell minus 0.059 upon the total moles of electrons that were exchanged. The electrons which you will cancel out, those will be the number of electrons that have been exchanged, and then log Q, where Q is your reactant quotient, So this is how you can apply the Nernst equation on both half cell as well as net cell reactions, and you can calculate the EMF of the cells. Only and only you need to know the E naught of cells. It will be given to you in the question. Okay, I hope you're clear with this. Very good. Now if you want to write it, you can write it, and then we'll move forward. I hope you've written it. I hope you've written this. I hope you've written this. Now let's apply the Nernst equation on a complete cell. Okay, so here is a cell, the epic cell, which we have been discussing for so long now, right? Yes. So from here, first we'll find out the anode and the cathode. We know that this is your cathode and this is your anode. So let's write the reactions as well. Anode oxidation, so zinc will go into Zn2 plus 2 electrons, and here since this is reduction, so you will have copper 2 plus, it will gain 2 electrons and you will get copper solid. Okay, yes. What will be your net cell reaction? You can write your net cell reaction here, my dear students. You have zinc to zinc 2 plus 2 electrons. You have copper 2 plus 2 electrons, and this will give you copper. If you see the net cell reaction, 2 electrons cancelled, you will get zinc plus copper 2 plus will give you zinc 2 plus copper. This is your net cell reaction. So from net cell reaction, can you calculate the reaction quotient? Yes, you can calculate the reaction quotient Q. That will be equal to products concentration upon reactants concentration. Copper is a solid, we will not use its concentration, we will use concentration of zinc 2 plus. Products concentration divided by reactants concentration. You have zinc solid, you will not use it, you will use the concentration of copper 2 plus. So this is the reaction quotient value. If I ask you what is the total moles of electrons exchanged, N. What is N? Ma'am, 2 electrons were exchanged, right? 2 were gained, 2 were lost. So total moles of electrons exchanged were 2. Okay, yes. So now can you write the Nernst equation? Yes. You can calculate the E naught of cell, which will be equal to E naught reduction potential of cathode. Which is your cathode? Copper. So copper 2 plus 2 copper minus E naught reduction potential of anode. What is anode? Zinc 2 plus 2 zinc. Okay, so this would be the reduction potential of anode. So these are the 3 values which you needed to know. Now you can write the Nernst equation. This will be E of cell is equal to E naught of cell. I hope you will put this value here. So I am just writing E naught of cell minus 0.059 upon, what is the N value? N value is 2. So here it will be 2 log, my dear students. Let's see Q value. Q is given here. Zinc 2 plus, and here it will be copper 2 plus concentration. So this is how you will be calculating the Nernst equation. EMF of the cell, right? Yes, perfect. If you want to write it, pause the video, write it, and then we'll move forward. Okay, so here you have a half cell. So now what you are going to do is, I am telling you that here reduction takes place. Here I am telling you that reduction takes place. So you will write the reduction reaction. You have H plus half electron and it will give you H2 gas. Okay. Now using the Nernst equation, this is your homework, my dear students. This is your homework. Using the Nernst equation, you have to write the Nernst equation for this half cell reaction. Okay. Yes. So this is your homework. Okay. I hope you will do it. Now, see, whatever I told you, all of the things are written here. You just can go through them. To calculate Q, the pure solid and pure liquid can be ignored. You know that for reaction quotient, you can ignore them. And the concentration of ions raised to the power of the stoichiometric coefficients must be in molarity. The concentration should be in molarity. In the expression of Q, the pressure of the gases in the atmosphere, but the concentration of the ions are in molarity. Okay? Yes. I hope you're clear with this. Okay, perfect, my dear students. So now, today, let's end this session. I'll give you a few questions as your homework and then we'll end this session. So this would be your homework question. Okay, this is your homework question. You can do this question. You are given the cell representation. You are given the cell representation and you have to calculate the EMF of the cell. So calculate the EMF of the cell, but this time, my dear students, just see. First you have to find the net cell reaction, then you will have to calculate the E naught of cell, and then you will apply the concentration Q part as well. Okay, so try this question. We'll be doing this question in the next class as well. Okay, try using the Nernst equation. I'm writing it here. You have to use the Nernst equation. Okay. Perfect. Try this and then we'll discuss in the next class. With this, let's end the session. So I hope you were clear with all the concepts today. I tried to make you understand each and every part with a particular example as well. So you need to practice a lot of questions. You need to practice your DPP sessions as well. Only then you will gain confidence and you'll excel in it. So we'll meet in the next session. All the very best. Thank you so much.